In this video, I'm going to be talking about how to solve an energy problem using the work-energy theorem. And this particular problem involves gravitational potential energy, kinetic energy, and elastic potential energy, which are three common types of energy that may be involved in one of these problems. Over here, we have a few different formulas. We have the PE formula, which may also be known as UG, gravitational potential energy. We have the KE formula, the kinetic energy formula, which may be known as capital K. We have a formula for friction for work, which would involve the cosine of theta if necessary. And then we have elastic potential energy, which is also known as UE. So in this problem, it's asking us about the final velocity of a 3 kilogram block if it slides 2 meters on a ramp and then compresses a spring 0.2 meters, and there is a spring constant of 55 newtons per kilogram. In this particular problem, it asks us to neglect friction. So if we're using the work-energy theorem looks very simple, and it basically just says work equals delta E, which is the change in energy. Now, you're solving a fairly complex problem with a very simple formula, and that's because that very simple formula gets expanded out into a bunch of different variables and numbers. So this is basically saying if there's any change in energy of this particular system, it'll be solved by taking the final energy and then subtracting the initial energy. Okay, so you can go forward with that setup. Actually, what I like to do is I like to add the initial energy to both sides. That way I have the initial energy plus whatever work is done is equal to the final energy. So because energy is conserved, all of that initial energy summed up should equal that final energy unless some work is added or subtracted from the system. So with that being said, I'm going to take that setup, I'm going to expand it out into all the different types of energy, and then we're going to see if we can cancel any of these out. All right, now I've taken the EI, the initial energy, and I just expanded out to the initial gravitational potential energy, initial elastic potential energy, initial kinetic energy, and then so on. Same thing for all the final energies. So I asked myself a series of pretty simple questions, and then I cross out the types of energy that I don't need. So my initial conditions are right over here. So it's the block sitting at the top of the ramp. Sounds like it's at rest. It's at the top of this ramp. It slides down 2 meters, an additional 0.2 meters, and then compresses a spring. So when I'm asking myself, does it have any gravitational potential energy? I'm asking, does it have any height above the lowest point in the problem? The lowest point in the problem is when the block compresses the spring, that 0.2 meters at the very end. So it doesn't really necessarily matter if it is slightly above the ground, which it is, because when it compresses the spring, it probably doesn't bump into the ground. You can take whatever is the lowest point in the problem and use that as your baseline, and then call that a height 0, and then anything above it, you would just call that, whatever your height is. Now, with that being said, that would mean that there is no height at the very end once it goes down the ramp, but there is some initial height, obviously, at the top of this ramp. For the elastic potential energy, is a spring compressed or stretched, or is there some kind of elastic type material that is compressed or stretched? In the beginning, there is definitely not. At the end, when it presses it down, there definitely is. So I'm going to go ahead and leave that UEF. And then for kinetic energy, is it moving or is it at rest? It seems like it's at rest at the very beginning, so I can go ahead and cross that out. And then we don't know if it's at rest at the end, but we know we're looking for a final velocity, so we probably want to keep that KF and see what happens to the velocity there. Now with work, is there any energy being added or taken from the system? In this particular case, I would say my system is the block, the spring, and then the earth, because the earth gives it the gravitational potential energy. Because there's no friction, heat being created, or any type of other variables in here, it looks like there is no work. So we can go ahead and cross that out. So all the types of energies that we're left with, we're going to take that and expand them out into the full formulas, and then go ahead and place all the numbers we know into those formulas, and then try to solve for our velocity. All right, so I expanded all my three types of energy out into the full formulas, and then I plugged in all the values that I knew. And you see that I left a blank here, and we can't have two unknown variables, or we wouldn't be able to solve for this final velocity that we want. And the thing that I'm missing is the height off of the ground here. So what I'm going to do is I'm just going to redraw a little triangle over here. So our block is at the top of this 30-degree incline. And according to the problem, the block slides 2 meters and then compresses a spring 2.2 meters. So it actually slides a total of 2.2 meters. So we can consider 2.2 meters our hypotenuse of the triangle. And we want this, I'll call it H over here, the height above the lowest point in the problem. So we can go ahead and use a little bit of trig and say that the sine of 30 degrees, so sine is opposite. So the opposite of 30 degrees is our h over the hypotenuse of 2.2 meters. Sine of 30 degrees is exactly 1/2. So when you multiply both sides by 2.2, your height comes out to be exactly 1/2 of 2.2, which is 1.1 meters. Okay, so I'm going to go ahead and put that 1.1 meters in for my h. Okay, so now I pretty much have everything I need. I'm going to go ahead and put this into my calculator, do the last little bit of algebra, and then solve for my velocity. All right, so I went ahead and I just plugged in all my values, and I just kind of cleaned it up a little bit. I multiplied these three to get 32.34 joules, multiplied these over here to get 1.1 joules, and then I took 1/2 times 3, which is 1.5, and then put the v squared right next to it. So I subtracted that 1.1 from both sides, divided by both sides by that 1.5, and then finished off by square rooting my value to get a velocity of 4.56 meters per second. Okay, now this is a very specific question, a very specific scenario. So when solving problems like this, or ones that are very different, the idea and the analysis is very similar. Starting from something like this, your initial energy plus your work equaling your final energy, expanding it out into a much more detailed version of it, and then analyzing the situation by asking yourself a series of questions like, is it above the ground? Is something compressed or stretched? Is it moving? And is there some other object taking or giving energy to the system that you identified in the problem? Okay, after doing that, you can go ahead and cross out certain types of energy If applicable in the problem, whatever you have left, go ahead and expand it out, put your values in, finish off with a little bit of algebra, and then that will hopefully lead you to your solution. So I hope that was helpful in helping you set up and understand an energy problem. Thank you for watching and listening.